Elementary classical mechanics is, as I said, sometimes called Newtonian classical mechanics. This name distinguishes it from what are called Hamiltonian versions of classical mechanics or Lagrangian versions of classical mechanics. These are actually the same thing as Newtonian classical mechanics underneath, but they're somewhat mathematically more sophisticated in the way they set out the same concepts. This Newtonian name also distinguishes the mechanics from relativistic classical mechanics, and of course, again, the Newtonian name distinguishes us from quantum mechanics. Throughout this course, as I mentioned, we are only going to deal with the non-relativistic quantum mechanics. And to be clear, by non-relativistic, we mean here that any particles with mass must effectively be moving much slower than the velocity of light. Incidentally, photons, the particles that make up light, they do have to travel at the velocity of light, but they have no mass, and it turns out we can still handle most of the physics of photons in quantum mechanics without having to deal with that explicit relativistic physics. Though, unfortunately, we are going to have to postpone most of the discussion of the quantum mechanics of light for some later time. Here then, we're going to start by reminding ourselves of some of the basic ideas from classical mechanics, including the ideas, as I said, of momentum, of kinetic energy, of potential energy, and of force, and the various relations between them.
For a particle of mass m, the classical momentum, which is a vector because it has direction, is p equals to m times v, where v is the vector velocity. So velocity has a magnitude, a speed as it were, and a direction, so it's a vector, and momentum is also a vector. The kinetic energy, which is the energy associated with motion, we can write as p squared over 2m. You may be more used to the version that the kinetic energy is 1/2 mv squared, that's mass times velocity squared divided by 2. These are the same thing in ordinary classical mechanics. In quantum mechanics, we generally prefer to think about momentum rather than velocity, and so we're more likely to write kinetic energy as p squared over 2m when we're thinking about the classical version. In this kinetic energy expression here, p squared over 2m, by p squared we mean the vector dot product of the momentum with itself. Now, potential energy is defined as energy due to position, as opposed to the kinetic energy, which was energy due to motion. And in quantum mechanics, we usually denote it by the letter capital V, even though this potential energy, which is in units of joules, joules being the unit of energy, might be confused with the idea of a voltage in units of joules per coulomb, because V is very often used as the letter to represent voltage. But here, in quantum mechanics, V is just going to be potential energy usually. But we will often use the idea of voltage in quantum mechanics, so we just need to remember not to be confused by this. Now, since potential energy is energy due to position, it can be written as a function of the vector position r. So we'll often see this, V of r. And we can talk about potential energy only if that energy depends only on where we are and not on how we got there. So if we look at this hill here and we put ourselves at some point on the hill, it shouldn't matter if we go up the hill and then back down again. The energy that we got on the way up, that we put into ourselves or the system on the way up, we got it back on the way back down, so we got back to exactly the same potential energy. The potential energy is only due to the position. Now, classical fields with this property are called conservative or irrotational fields. That means without a kind of rotational aspect to them. And in that case, the change in potential energy going round any closed path, as we just did when we went up the hill and back down again, is 0. Not all fields are like this. And for example, if we had a vortex-like field, then that would not be true. In a vortex field, such as the bathtub vortex you get when you drain water down the bathtub drain, has a rotational sense to it. So if we had some vortex-like or rotational field, if you went round in one direction, it might take you a lot of work to go round that path, but perhaps in the other direction, the field would do work on you. This is often encountered with various effects associated with magnetic fields, for example. We can get kind of rotational effects in them. Now, this obviously would not be conservative because the energy you have at this point here doesn't depend only on where you are. It depends on your past history, and in this case, whether you went round a circle this way or round a circle that way. But there are many conservative fields, and good examples are gravitational fields, and in particular electrostatic fields, and we'll often use those as we discuss quantum mechanics. But as I said, various fields are not, and some of the effects associated with magnetic fields are not conservative. The total energy can be written as the sum of the potential and kinetic energies, at least if we're working in an irrotational field like gravitational or electrostatic one. And when we write this total energy out as a function of position and momentum, it can be called the classical, in this case, Hamiltonian. That's a historical reason why it's called this, after a gentleman by the name of Hamilton. And for a classical particle of mass m in a conservative potential V of r, then the total energy, of course, is just the sum of the momentum squared over 2m plus the potential energy V of r, that is kinetic plus potential. And as I said, when we write this energy in terms of momentum and position, we can also call this the Hamiltonian. Now, we'll come back to this later on. For the moment, we just need to know that it's something that represents the total energy of the particle when we express it in terms of momentum and position.
Note, incidentally, that the zero, or the origin we use for potential energy, is always arbitrary. We can choose it to be what we want as long as we're consistent about it. In both classical mechanics and quantum mechanics, there is no absolute origin for potential energy. And in fact, we only really work with differences in potential energy between one position and another. It makes no difference to any problem either in classical mechanics or quantum mechanics at what position we say that potential energy is equal to zero. Again, as long as we are consistent all the way through a problem, we have to use the same zero. We do typically make some specific choice in practice, and we do that often just to make it easy to do the algebra in the problem of interest.
In classical mechanics, the idea of force is a very important one. We often use this concept of force, and Newton's second law relates force and acceleration. So you may remember the force as a vector equals the mass times the acceleration. So if you push on a mass, it will start to accelerate. And how fast it accelerates is dependent on how much force you put on and how massive it is, of course. So m is the mass and a is the acceleration, and it's a vector. Equivalently, we could say that the force is equal to the rate of change of momentum.
We do find behavior that corresponds to Newton's second law in quantum mechanics. But we don't use Newton's second law as the way to start quantum mechanics. And in fact, in quantum mechanics, we seldom use the idea of a force directly. We can express the same idea by thinking of a force as the gradient, the slope, as it were, of a potential. And we'll set up our quantum mechanics more using these potentials instead of the forces directly. To understand the relation between force and potential energy, suppose that we're trying to change the potential energy of a ball by pushing it slowly and frictionlessly, in our idealized view, up a hill or a slope.
So let's look at a situation where we have a slope here, sometimes called an inclined plane in classical mechanics. And we imagine we have some ball that we're going to push up the hill. So we're going to push it through a distance delta x, and we're going to be pushing with a particular magnitude of force here F push x. So to push this ball up the hill here, we're going to exert this force. And as we do this, we're going to get a change delta V in the potential energy V. And that is going to be the product of the amount of force that we are pushing with times the delta x, the amount we change the position in the x direction as we move up the slope. So the change in potential energy is the force times the distance, all in the same direction. Equivalently, we could flip that formula around and say that the force is the same thing as the rate of change of potential energy with position. And here we're imagining we're doing this very slowly, so there's no kinetic energy involved with this. So the force is the rate of change of potential energy with position here, the delta V over delta x, or in the limit we could write that as dV by dx, in the limit of very small delta x. Now, the force exerted by the potential gradient on the ball is downhill. In other words, we think here that gravity is trying to push the ball down the hill. So the relation between the force from the potential energy is minus dV by dx. We were pushing uphill to counteract the force that comes from the potential energy, which was trying to push the ball down the hill. So the force associated with the potential energy itself is minus dV by dx. We had to push uphill to do some work to change the potential energy. We were pushing against the force that comes from the rate of change of potential energy. So that force from the rate of change of potential energy is minus dV by dx. Now, so far we've only been thinking about force in one very specific direction. Of course, force is a vector, so we have to think explicitly about directions. And we can generalize our idea of the relation between potential and force to 3 dimensions with force as a vector by using the gradient operator. So the gradient operator, you remember, is gradient of V or grad V. The gradient is constructing the 3 components of the force, one in the x direction, one in the y direction, and one in the z direction, using the partial derivatives. Partial dV by dx is the component of the force in the x direction, partial dV by dy is the component of the force in the y direction, and partial dV by dz is the component of the force in the z direction. And these all add up to give us our more general 3-dimensional relation between potential and the force associated with it as minus the gradient of the potential.
So this completes our basic revision of elementary classical mechanics. As I said, we will be using many of these concepts, especially the kinetic and the potential energies and the momentum, as we start to set up quantum mechanics.